Hello. So I would like to talk about potential new applications of lasers. So while we think about lasers as they are as causing the excitation of target, turns out that they can also cause de-excitation. For example, in STED microscope, well known, like here, there are used two lasers. So like here, so one is excites the target, the blue dot. Then you would like to de-excite in this donut shape round. So finally, thanks to the excitation, the final dot is smaller, so it allows for better resolution. Yeah, so one diode laser excites, the second diode laser de-excites. So I would like to propose a few more applications of laser causing de-excitations. So usually there is lasers tend out to have a built-in optical isolator. So it removes some behavior. I would like to convince you to that is very interesting, that it could have many applications. So here is, let's say, his laser. Here is the optical isolator, which allows for photons only go toward right from laser toward target. But we believe that the physics is governed by this CPT symmetry, that performing this symmetry, the equations governing physics are the same. So after this symmetry, the photon trajectory would be reversed. So you'd get this kind of laser with reversed optical isolator. So what seems promising, so I'll try to convince you. For example, here is the original approximation of two-way quantum computers. So standard photonic computer, quantum computer, has this photonic chip for which we usually inject some photons with lasers. Yeah, so then we measure finally the outcome. But for two-way, we'd like to control it from two-way, the photon evolution. So we could put second laser here, and now each laser is a resonator. So now we have coupled two resonators and the photonic chip between them. So intuitively, it is slightly stronger than standard setting. And from this perspective of the CPT symmetry, we reverse the photon trajectory, and now we inject the photons from this laser. Yeah, so we kind of both push photons into, but also pull photon from the chip. So we have two-directional control, and if possible, it in theory is much more powerful from computational perspective. For example, allowing to solve NB problems like cipher breaking. I will also talk about this application. Okay, so generally, electromagnetics and hydrodynamics are governed by very similar equations. So like here, so we can see that there is some analogy. So the behavior should be quite similar, and we should be able to transfer some properties. So for example, while we think about lasers that they are causing heating, turns out there is also optical cooling. Why naively only laser can push target, there are many ways to do optical pooling, also tweezers, kind of both. Finally, the radiation pressure is a vector. Yeah, so it can be toward the surface, it's positive, like we could think of, but it can be also outward the surface. Yes, so we can get negative radiation pressure, and there are indeed many articles about negative radiation pressure. So let's think about computational perspective. So having this electronic chip, the battery both push electrons but also pulls the electrons. It acts from two ways. Yeah, so pushing electrons, pulling electrons. Very similar is this microfluidic chip, and we have a pump which both push now some fluid and pulls some fluid. Yes. So as there is similarity between electromagnetics and hydrodynamics, we could do it for electromagnetics, for example, for microwaves. So it should also, this analogy should also work for microwaves. And finally, then the most convenient would be doing it on photons. So we need some analogy of pump for photons. And there are many reasons to think that ring laser is such analogy. So in ring laser, we enforce photons to circulate in one direction. Yeah, so thinking about this ring laser, it injects indeed the photons into this let's say quantum photonic chip, but looking from perspective of CPT symmetry, we reverse this photon trajectory, and now we inject the photons from the opposite side. Yes, so we act from both directions, we kind of both push and pull the photons. Or the opposite from the CPT perspective, push and pull. Also for these two, from the CPT perspective, you would reverse the flow of electrons or the fluid. Yes, so we should get this two directional controlled chip. Okay, so this CPT symmetry is believed to be fundamental for physics. That so it has charge conjugation, parity, and time. Here is example for electron. So it is required for the quantum field theory if it's already invariant, Hamiltonian. So it has to be CPT symmetric. If there would be variation, if, for example, the Lorentz invariant would be crashed, so it would be very bad for the fundamental physics, if it would turn out that the CPT symmetry is wrong. There is this Feynman-Stackelberg interpretation that antiparticles are kind of travel back in time. Then there are many tests, experimental tests. Here is a good article. The slides are in the link. And so, but they are all microscopic for single particles. So the big question is CPT symmetry still valid in macroscopic settings? So the applications can be also, I would propose, can be also thought about as tests of this macroscopic CPT validation. And the symmetry that it should work is also here. Yeah, so the equations are very similar for electromagnetism and for hydrodynamics. So it should be there shouldn't the time symmetry should be maintained. If there is why the CPT symmetry believed to be at heart of physics in the equations, from our experience we see the asymmetry. Yes, we can clearly distinguish future and past. So and there is in this more formally there is the second law of thermodynamics that the entropy grows toward our future. However, so how to is it a problem? Is it a conflict between them? So symmetry and asymmetry. So here is such nice example that there is no problem. So we have a surface of lake which from a fundamental equation perspective is symmetric. However, if you throw a rock, there is asymmetry in the solution. Yeah, so it's not a problem that we have symmetry in equations, but asymmetry in solution. So it's a very common situation. And the big question is what was this rock here which created this entropy gradient we are experiencing? I think the Big Bang is a good candidate to think about it because everything was localized, so entropy was low, so it should create the entropy gradient we are observing. So now let's go back to these photons. So the very nice symmetric phenomena is this the Rabi cycle that we have laser in theory and some atoms, and this laser causes periodically excitation, deexcitation, excitation, deexcitation. In practice, it is damped. So, but if you think about, so we have two resonators. Laser is a resonator. Atoms are tiny resonators, isotropic, and they exchange energy. Yeah, so once the photon should go there, but then should go back. So this laser causes excitation and de-excitation, excitation, de-excitation. And you have these two equations, absorption equation and simulated emission equation, which changes sign if you switch time to negative time. Yes, so the N2 is number of excited atoms. Here in absorption it grows, or in the ground atom it shrinks, and the opposite for simulated emission. And they are governed by the same Einstein coefficient B12. So we can also figure as argument for CPT symmetry because they are the same equations if we look from CPT perspective. Okay, so here is a nice. Maybe let me switch to some animation. So here is this animation from Wikipedia. So we can see that we have two resonators here, pendula, and they are coupled by this wire here, and they exchange. So now one has energy, then it gives this energy transfers to the second, and so on cyclically. Yeah, so we can think that the Rabi cycle is approximately something like that. Yes, yeah? So we have this coupled pendula given by let's say approximately this kind of equation. Rabi is given by similar. In practice, there is damped Rabi that it loses these oscillations, and there are many articles claiming that they are very similar. So we can think about Rabi cycle as coupled oscillators. Yes, like here I presented previously. So, however, there are ways to diminish this exchange, like these optical isolators can forbid one direction of photons. Yes, and a simpler example is free electron laser. So this synchrotron radiation I'll show later. But so there is this nice so if there is dim-ish, if we cannot make a transfer in both directions, so there should be some problem with these Rabis. So so I was searching for this synchrotron radiation, and it turns out that there was this article that says that that previously that they have tried to get Rabi cycle with free electronizer, but they failed. And finally, they were able to get the Rabi cycle, and they showed this plot that there is one Rabi cycle and so on. But what we can see that the excited state is there are these two peaks, but the ground state would be in the center. So we can see it gets to nearly only excited states. However, in damped Rabi, you should get to 1/2. So it really is not 1/2. So they have shown that there is some shock response at the beginning, but finally it goes to the nearly completely excited state. So there is so here it is damaged. So they were able to separate, use only the blue line, but remove the violet thanks to this synchrotron radiation. So the question is, are there different ways to separate it, similar like optical isolator, or can we do it the opposite? Have only the violet, but remove the blue one. So it would lead to many applications I'll talk about. Just having just the violet one, not the blue ones. So for example, it turned out that lasers, the laboratory at least, have usually built-in optical isolators. Yeah, so if you have this box, it probably have this optical isolator inside. So it would, as said here, it would make problematic Rabi cycle because it forbids this photon, the violet photon trajectory, the optical isolator. Yes. So in my view, we should be able to do this direct approach for direct Rabi realization. Due to this optical isolator, it makes it more difficult. So I have looked through literature how they handle it. Do they remove this isolator? And turns out that I found two approaches. So one is adding resonator, additional resonator. Yes, like here. So here is a diagram, simplified diagram. So we can see that the laser pumps this resonator, and the Rabi cycle is between this resonator and the final atoms. Yeah, so they have overcome this optical isolator by adding this additional resonator. And the second approach in this article is Mach-Zehnder. So we can, while here we have exchange of photons in one left, right. Here it is done instead. So here are the blue ones, but looking from CPT perspective, they are here. So now the blue goes here and the violet goes here. Yeah. So it's tricky, but doable to also get Rabi cycle with laser having this optical isolator. However, probably the much simpler way would be just trying to remove this optical isolator, yes, and have the direct approach. What might be practical, for example, in quantum computers, Rabi cycle is often used. Okay, so how to get this only violet? Yes, so that we have only not pushing photons, but only pulling photons, as in CPT perspective. So this is the most optimistic approach that it hopefully it should work. So it's difficult to test because nearly all the bot lasers have this isolator. So it's not usually not modular, but the best would be to get out and turn and put in, but producers did not probably predicted this application. So hopefully in the next generation of laser, it will be easy to do. Just take out, rotate, and put in to get this kind of laser. And if it will not work, so maybe I'm not certain about this. So this is the cheapest, the simplest, but the least safe approach to get it. So here are safer approaches. So one is this ring laser, as also mentioned, that due to this optical isolator, we enforce the photons to rotate to circulate only one direction. So now they excite this target, but looking from CPT perspective, the photon trajectory would be reversed. Yeah, so they would circulate the opposite direction. So they should excite this target toward negative time. That means that they should cause deexcitation of this target toward positive time. Yes. So indeed, this this laser, if you put target here or maybe here in front of this violet, it should cause de-excitation if CPT symmetry is right in macroscopic setting. Yeah, so so we have these two equations and you just switch them, changing this perspective to this in practice only team. And finally, the synchrotron radiation. So here is this free electron laser I have mentioned, simplified. So due to its magnetic fields, we enforce electrons to travel to this sinus-like trajectory, and synchrotron radiation produces these blue photons. However, from perspective of CPT symmetry, this electron or positron trajectory will be reversed, and it produce photons toward left. But so it would cause excitation toward negative time, so toward positive time should cause de-excitation. Yeah, so this is the safest approach. So if it doesn't work, I don't know how to say CPT symmetry. Yeah, so maybe this approach will not work. So but it would, if none of this will work, then CPT symmetry has to be broken, and it would be also very interesting as it would require to rewrite the fundamental physics. Yes. So hopefully at least one of them should work. I hope. Okay, so let's think about applications. Yeah, so here is one of them. So we have this, let's say, ring laser for simple applications, and the CT computer tomography measures absorption coefficient. So we have some source, some lamp laser, and then there is this target you'd like to measure. And then there is detector, which should be cooled. So we have in a low energy state detector, and then we take a look how many atoms would be excited, and based on that it's subtracted by this, let's say, integral of ground state atoms in this spectrum on the way. So we can get this absorption over this line. So now having multiple such pixels and doing it for multiple directions, there is this random transform, and thanks to that, a CT scanner gets three-dimensional map of absorption coefficient. In practice, of some gammas, Röntgen, but now, okay. So now let's make CPT symmetry of this picture as physically CPT symmetric. We should also do this way. So what's happening? So here we have to reverse the photon trajectory, yes. And so now the photons will go here, and as mentioned, we would have to put the target for the photons in the opposite direction, yes. So here is the target, and now it should cause de-excitation of this target. And to as a detector, we need to make it excited. We need continuous pumping of this target. So there are many ways that can be used: second laser, electric, like in semiconductor optical amplifier. So could be semiconductor with electric excitation. And there are many ways, but this is difficult part, and also monitoring population. However, there is a hope for simpler realization. I will mention in a moment. So now it should, instead of subtracting N1, it should subtract N2. So why it's better? Because N2 usually it's much smaller. So there are excited atoms on the go, or this is ground state atoms on the go. So usually the excited is like 100 times smaller. So the transparency should be much better. Yeah. So like for visual, like it's 1-2 centimeters into body. I hope it should be meters into the body. So it needs to be checked. So we would be, if so, we could make 3D maps, like performing the CT scanner of like this, of absorption, of not absorption, but of emission coefficient. We should be able to make 3D maps of emission coefficient. But so inside body, it turns out there are many molecules which are excited through chemistry. For example, so here is the absorption coefficient for some molecules, and here is the biomolecules, here is the emission coefficient. So for example, NADH is crucial for the metabolism. So making this kind of scanning 3D map of around this 460 nanometers, hopefully we should get more or less an NADH map in the body. Yeah, so and make it multiple frequencies. I hope it should be, so it would be hyperspectral CT, emission CT. So hopefully it should allow to get very, very precise maps of 3D maps of tissues and also pathologies like cancerous tissue. So it is very, I think, promising for medical scanners. So inexpensive, maybe low size, and very high resolution, both in time and space. So it looks very promising for scanners, for medical scanners. Okay, so similar application is trying to cause deexcitation. Yes, so we just would like to shoot like here, hopefully this way, or maybe some ring lasers, or maybe synchrotron radiation to cause deexcitation of something. So STED microscopy is such example, and instead I think we could improve STED microscopy by so they are complaining that there is photobleaching in STED microscopy because of bombarding with photons. So I hope just rotating this optical isolator, and it should no longer make this photobleaching. So I think we can improve STED microscopy by just rotating its optical isolator. Okay, so let's think about so probably some chemistry applications, maybe some 3D printing, and finally, I think that the medicine application will be very interesting, especially due to this hopefully the transparency we should get. Yeah, so for example, this NADH is pushed out from metabolites. So if you would speed up the excitation of this NADH locally, then hopefully you should starve this tissue. So you like to make like here that we starve this tissue, not damaging tissues on the go. So for example, you have a line of lasers, and we rotate them being around some this axis. So this way, I think we can get orders of magnitude smaller dose here than here. Yes, and this is very non-linear behavior. So hopefully you should only starve this tissue, but don't do anything to this tissue. Yeah. So besides starving, also heat up, because this energy, instead of being transferred to some other chemical, it will be released as photons. So and finally into heat. So also heat up locally. So I think there could be many applications. So here is just radiotherapy of cancer, but probably some metabolic problems could be attacked this way, because there are many molecules which are autoluminescent, which produce photons themselves due to chemical energy from chemistry. So probably there could be perform multiple types of therapies. Or maybe this thing that oxygen is also interesting, is toxic, and it's created various situations. Okay, so another, so how to realize it, test it. So here is some article which has a similar setting in fiber optics. So here is a laser, and here is excited erbium, and this laser literally pulls these photons to go left and then down to this detector. So it looks promising, and also we can see that there are optical isolators everywhere, but here, maybe due to the simulator, but so this is one way to test it, but the difficulty here is having a laser without optical isolators, so what is kind of non-trivial, because you need modular laser or some just diode plus drivers. So this is a promising direction how to do it. So it's called backward assay amplified spontaneous emission in the literature. So it is well known, but usually removed with lots of optical isolators, which removes this effect. I would like to convince you that maybe it's worth to exploit instead of removing. Yes. Okay, so thinking about this kind of setting, we can think about better this backward camera, this camera for this scanner. Yeah, so here we have the standard CT, forward source, the target, and the detector camera for absorption coefficients, and here is for this backward for this emission coefficients. Hopefully a better transparency. The question is how to make this camera. So here is some approach. So if this works, so maybe you can just pump some surface like a display screen, and now we put this semi-transparent mirror, and here is the main matrix, CCD CMOS matrix. So hopefully this should work for practical such scanners as this camera. So this is one direction, and I think also it might be interesting for example, for astronomy, because it needs a target which pulls photons from us. So it's not very common in nature, maybe. However, as mentioned, the synchrotron radiation is optimistic that probably it happens then. And for example, in pulsars, it has ions in very high velocity, so it emits synchrotron radiation, but so we should also make this symmetric pulling. So at least pulsar should be visible, hopefully by this camera. So probably many more objects with many surprises. I hope there will be building such a camera. Okay, another applications could be backward lighted camera. So now the standard camera, but kind of lighted with this backward beam. Yeah. So this laser tries to increase the excitation of the target, and so to make it easier to get light for some thermal imaging, for example, but also attacks on quantum cryptography, because there is usually use a laser which tries to work on single photons. But now we could make it to produce more than one photon and try to steal some of them. Yeah, so I think it could be used for attacks for the quantum cryptography protocols. Okay, so another direction, maybe more controversial, is that there are a few articles claiming response of system before the impulse. So here is usually some group wave velocity, but finally there is response before the impulse. So here, for example, so here is the impulse, and here is measurement between this and this route, and based on parameters, they can, for some parameters, they get negative delay. Yeah, so kind of response before the impulse. And here is the recent one with many news stories by the Steinberg group. So here is very simple setting. Also, again, the rubidium cell. So here is the seeing the photons, and there is selection based on these photons, and here is continuous wave probe. And again, so one is without post-selection, and one is with post-selection. So with post-selection is stronger behavior, but without post-selection, they still get behavior. Yeah, so still they can see something is happening before. So they say that photons spend negative time in the medium, the rubidium cell. So I think it's not very physical, spending negative time. So I think what's happening is that this laser excites this laser of the magneto-optic trap excites some of the atoms, and there is happening this stimulated emission, which should have being CPT symmetry analog of the excitation should have opposite also delay. So I think this is not like this picture, but later like this picture. Okay, so here is some textbook view. So in textbook we have these three types of situations in optics. One is spontaneous emission in a random angle. Then there is absorption from concrete angle from this where this photon comes from. And also in textbooks there is this picture for the stimulated emission. Yes, that we have one photon and kind of knocks out another photon. Yes, from the excited target. However, CPT symmetry suggests it should be this picture. Yeah, so just from CPT perspective, it becomes this picture. So the question is, which is wrong, this or this? And I think both are true, because so this is required by CPT, and this should be consequent. So it should be also required. So here is some explanation. So here is this scenario. Yeah, so one photon goes here, and now you have two photons. So after performing this time symmetry, we have this situation. So what's happening? So if this is true, then indeed this deexcitation pulls photon, but it cannot pull from here, because so ground state is kind of transparent for this pulling of photons. So it pulls photons from here. Yeah. So this laser pulls photon from here, but some of these pulled photons are absorbed by the medium. And CPT symmetry of this view indeed gives this textbook view. Yeah, so first I thought that only this is true, but now I believe that both are true. That this is the fundamental required by CPT symmetry, and this is the consequence, which is like here can be indeed explained as a consequence. And also this kind of picture shows that we should think about these scanners, these computer tomography scanners, also for absorption. So if there are excited targets on the way for absorption, there should be some addition. So it's more complicated. So usually for these very high energy photons used now, it's not a problem. But here we should have it in mind. So it kind of it should enhance. So it's more so sophisticated for CT scanner. I think I think we should just work on this density being real numbers, not just positive, but real numbers, and it should bring some maps which are not exactly an NADH, but more complicated mixtures of multiple molecules and the excitation levels. But basically, I think it should do, and having multiple frequencies, we should get three-dimensional maps of tissues easily. Okay, so now let's go to the final topic of this two-way quantum computer. So here is my first slide of two-way quantum computer talk. So I've shown a few approaches with lasers, just one laser pushes, second pulse, but there are also many different ways to try to realize. So we need this typical symmetry says that if you have state preparation, there should be also this symmetric version. So I call it post-paration. Yeah. So like preparation, but not fixing the initial state, but the final states. So to get it, we should just recreate the process used for the original state preparation, but reversed. Like these lasers with reversed optical isolator hopefully should work. Or there are different ways. For example, if here we just perform impulse for state preparation, this silicon quantum dots approach. So we just need to perform opposite impulse at the end. And from perspective of CPT symmetry, we have performed the original state preparation. Yeah, so I don't see any reason why it shouldn't be possible, but you just need to use these symmetric formulations. So not just Schrödinger, but later Feynman path and path integrals that we fix initial and final values, and like in scattering matrix, we assume Feynman ensemble of possibilities between them. Okay, so here is some in Wolfram quantum framework. So in standard quantum computer, one way you have state preparation, there's some unitary evolutions, then measurement. And in two way, we additionally can use this post-paration, yes, the symmetric, this conjugated version of state preparation, and it works so it practically it works as post-selection, but with higher success. So post-selection has probability 1/2, no, approximately to be successful, and here it should be nearly always successful. So, but having many qubits, the probability of success drops exponentially, approximately, and here it should be nearly constant. So optimistically, we get exponential improvements, speed up. Adding this one operation, this reverse version of state preparation. Okay, so this was the original way of research, and we have made we have found some team. We got these quantum interns for these topics. There are multiple articles in these two-way quantum computers. No, again, it requires some experimental. Maybe from photonics, I try to fight from photonic direction and from superconducting or different technologies. For all of them, there should be some way to do it. So, for example, maybe let's look. So, for example, for superconducting and more general, is for superconducting, you perform state preparation by just lowering temperature. Yeah, so there is very low temperature, like 30, 20 millikelvin. So we can assume that everything's the ground state. Yeah, so here is in the ground state. Then we perform some operation. Then we measure. But physics is CPT symmetric. So unitary evolution is symmetric. So from this perspective, the temperature is the same. So there should be also ground state at the end. So looking from this perspective, you should be also able to perform this evolution. Yes, so the readout is very invasive process here. So it should still work. And finally, so here is some two-way quantum computer situation. Yeah. So here we don't do anything with this qubit. So naturally, it should radiate this energy. But looking from CPT perspective, we start with zero. We start with the ground state, and we evolve inside with ground state. So it should be the same as here. I don't see the difference. So hopefully For example, for superconductor, it should be relatively simple to realize, maybe with current quantum computers, and having such two-way quantum computer, so we could solve NP problems as mentioned. Yes, so in NP problem we find input which satisfies some verifier which costs a polynomial time. So, for example, the TSAT is this one of these basic problems, and they are equivalent. So, if we have solution for one of them in polynomial time we could solve any other. So here is this TSAT problem next. So we have some alternatives of triples. Some of the variables can be negated. And the question is there are there values for which all of these triples are true? So the problem is that while testing is easy, yeah, so it's polynomial time. Yes, however, the number of inputs is exponential. So that's the difficulty. So the question is, could we find the best among exponential number quickly? Yes. So in time, in polynomial time. Yes, that's the goal. So here is some solution. So but if being able to do it, I think many ciphers could be endangered, because so to break a cipher, so cipher takes this encrypted data, takes key and decrypts it. So for proper key, it decrypts in some reasonable. For improper key, it decrypts into noise. So this verifier for cipher breaking would be, for example, if decrypting some beginning of the file with this key, do we get noise or something with smaller entropy, for example? Yes, so it would be this kind of verifier trying to decrypt the beginning, check the entropy, and if it's lower, then it's okay. If it's high, then it's wrong. So in theory, many ciphers could be endangered if getting these two-way quantum computers. But also there are positive news. So global optimizer. So it's easy to get the local minimum, but the global minimum is difficult. It's because we have exponential, pessimistically number of minima. So having an NP solver, we could ask if the function has minimum below some threshold, and then we change this threshold to get this minimal value of this function. So we could make global optimizers, for example, for drug design, to find a drug which is the best for some features we would like to get for the graphs. So I think it would be very, very interesting for drug design, algorithm search. So the verifier could make some finite run of some part and check how good it is in some evaluation. And also, two-way quantum computers in theory allows for much better stability error correction. There are many new error correction approaches. So for example, we have so there is mid-circuit measurement for error correction, quantum error correction, that we measure some qubits. So in two-way quantum computers, we could do mid-circuit postparation, that we fix some qubits to, let's say, to 0. Yeah, and doing so, we can enforce it that we work only on code words. So we have quantum superposition only of code words which are very far from each other. So it should be much better for stability error correction. So I think also from error correction perspective, it could be many improvements. Okay, so how to solve NP problems having two-way quantum computers? So here is some simple situation. So as in short, so maybe let's look at short. So for short, we make Hadamard to get this all possibilities like here. Yeah, so here is also in short. Then we perform in short this classical function. It is in short algorithm, and then we just measure this classical function in short, and then perform some quantum field Fourier transform, and it gives us a hint for the factorization problem. For now instead of measurement, we can perform this postparation. We can enforce it to some value. So for example, we can use here the verifier. Yeah, so here generally would be the verifier which tests if given A is true. And now we would like to enforce this verifier to be true. Yeah, so it should rest in the ensemble to only satisfying the verifier. So now measuring it, we should get one of the, ideally, you should get one of the solutions to our NP problems. Yes. So here is again, so here is the Hadamard. Here is the classical function for TSAT. There are these alternatives with negations. Now we'd like to enforce all these alternatives to be true. and each fully should restrict this ensemble to only solutions of our NP problems. Okay, so let me finish. So it looks like the optical isolator, which is built in nearly all lasers. So there are reasons for that. Yes, so they say that if you don't have isolator, it's easy to burn the laser. So it removes some very powerful behavior. So now let's maybe, instead of removing this behavior, maybe let's try to exploit it. Yes, so for example, by just reversing this optical isolator, or maybe using synchrotron radiation. We have this backward beam which does not excite target, but only de-excite target. Yes, for example, for STED microscopy without bleaching, by just reversing its optical isolator. Or maybe that direct Rabi, that by removing this optical isolator, that's also, as mentioned, it should allow to do it without the tricks like this additional resonator or Mach-Zehnder. Or causing the excitation only, for example, for the radiotherapy as mentioned, yes, that we could try to starve the cancer by deexciting NADH or some different molecule locally, or some chemical processes speed up backward camera of backward beam for this CAT scanner, for example, or maybe some astronomical observations. Because lighted cameras, I think also medical applications, maybe different ones. This emission computer tomography, especially hyperspectral, backward beam through backward camera, I think it should give a very detailed tissue map with all the problems. Finally, two-way quantum computers, like here that we have laser, one pushes inside and then pulls out, and from CPT perspective, it does the opposite. Yes, so now we inject here, here we inject here. Yeah, so we both pull photons into or pull from. Or different perspective is that we have coupled resonators. Yes, the orange one, they are coupled, but on the way there is this computational chip. Okay, thank you